morning, good afternoon, good evening to all of you wherever you are in this part of the globe. And this is the data analysis and decision making course 3 under the NPTEL MOOC series. And as you know, this total course duration is for 12 weeks and the number of contact hours is 30, which when broken down into lectures is 16 number, considering each lecture is for half an hour. And as you can see from the slide, we are in the lecture number 54, which is the 11th week, the last but one lecture for the 11th week, and each week we have 5 lectures of half an hour each. After each lecture, the week, you have one assignment to do, and you have already completed 10 assignments. You will undertake and also do the 11th and the 12th and then the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are considering the concept of very basic background of stochastic programming, reliability optimization, robust optimization. And there I started by saying in stochastic programming, obviously you will consider that the underlying distribution of the parameters which are unknown, or the decision variables which you want to find out are unknown. But in case if they are unknown, obviously we will try to take the recourse of some statistical simulation techniques, bootstrapping, jackknife and so on and so forth, and then try to basically find out the best estimate using all the trying to verify the properties of the estimate with respect to the population parameter and complete your job, and utilize those estimated parameters of the population, which are the estimates from the sample, and proceed. In case they are known, you basically directly use them. So, where are they to be used? So, let us consider that in the stochastic programming and the reliability programming concept, while in the robust programming concept or robust optimization concept, we consider some perturbations like an atom vibrating about its nominal value in mean value, and there the underlying distribution is not given or not known, or that is not considered at all. We consider the concept of some perturbation sets, and depending on the perturbation sets, we basically proceed to find out some proofs of or the greater than type, less than type. What is that? I am going to come to that later. Type of proofs for the constraints on the objective function. In the objective function, obviously it can be done as a minimization or maximization, to which also I will come later on, and then we proceed by the simulation concept. Now, if you remember the last lecture, which is the 53rd lecture, I drew a lot of diagrams in order to make you understand that if it is normally distributed univariate, then trying to basically use the standard normal deviate, the Z table values and the standard normal distribution values, we can basically solve the problem depending on the level of confidence or alpha which you have. Now, when if it is a multivariate normal distribution, obviously you will use the concept of multivariate normal distribution, you have already the proofs. Then again the concept would be utilized in such a way that both the variance covariance matrix, the n by n matrix, considering there are n number of such decision variables are there, provided the parameters are not to be considered now. So, you will basically consider the n by n matrix of the covariance matrix of the decision variables, the vectors of the means of the decision variables from the underlying distribution, and proceed to solve the problem. Now, when you want to solve the problem, I mentioned that in the reliability concept you use the sequential optimization technique and use the most probable point technique. So, what you are trying to do is that you are trying to basically consider the probability that the function here I am going to consider any one of the constraint arbitrarily, say for example g, and g is a function of x, which is the decision variables, d which is the deterministic parameters, p is basically the probabilistic parameters, and we will consider g as less than equal to 0. It can be greater than equal to 0 also, it can be less than equal to, greater than equal to b 1, 2, 3, 4, whatever the right hand side of the equations are. And this is true with the probability alpha, which is the level of confidence. Then when we consider the diagram for the normal distribution case, it will be on the right hand side or the left hand side for the diagram, if you remember, depending on how the problem formulation has been done. And when the problem formulation has been done, what we do repeatedly is that solve the optimization problem using any of the known techniques in the x plane or the x space, then try to basically transform that actual output which you get the first iteration into the u space, then optimize trying to find the minimum variance point or minimum most probable point, and then basically do the inverse transformation of that u star point into the x space and continue doing the optimization, and then back and forth you continue till you basically are able to reach the optimum solution depending on the iterative process which you are trying to aim at. Now, a question which would have occurred in your mind as we were discussing is that what is the point do we consider x naught from where we start. So, you saw in the steepest descent approach in the problem which you solved, the x naught was considered as an arbitrary value, it can be chosen intelligently also. So, in the using the same concept that you have to use an intelligent starting point for your search, we consider the mean values or the nominal values for the vectors x. So, x distribution vectors which you have, which are mu 1, mu 2, mu 3 till mu n, considering mu 1 is the expected value of x 1, similarly mu 2 is the expected value of x 2, and so on and so forth. So, we will basically consider the mean values of the x's. In the similar way, we will consider the deterministic values are deterministic. So, they are fixed. So, there would not be any mean values for them, and for the parameter values which are non-deterministic p, we will also take the mean values, and then basically try to start off the optimization in the x space. Now, the question is that, well, you have considered the normal distribution, and as I showed that in the normal distribution case for the 2 dimension, if the variances are equal. So, hence the normal distribution, if it basically is rising from the x axis x 1 and is coming from the orthogonal direction y, which is x 2, and if they basically converge, then the overall area is a circle, provided the variances of both are same. In case the variances are different, you will basically have an ellipse where the major axis and the minor axis would be accordingly like this. In case if the variance of x 2 is more, then the major axis will be vertical. In case if the variance of x 1 is more, the major axis would be a horizontal line. So, obviously, it would mean that it is basically like a baseball in a 3 dimension case, provided there are 3 random variables, and also consider that the variances of 2 of them are equal, 1 is more. So, in that case you will have a baseball lying horizontally on the field or vertically up on the field. Now, in the case if the variances are all equal, then we basically will have a sphere, and in the higher dimension case it will be a hypersphere, or how the figure is done, considering they are the set of symmetric distribution of the normal distribution which we all know, and based on which we can solve it quite efficiently. But now the question happens, and or the question arises is that what happens if the distribution per se are not normal. So, let us consider that example here, and I have drawn the similar figure, but with a major change here. So, the major change is what I am going to come to that later on. So, consider the x axis is x 2. So, you are taking x 1 and x 2 does not matter. Along the y axis I am measuring x 1. So, this and the first green line which is marked as the first constraint, which is say for example G 1. The second constraint is also marked by the green line, which is the second constraint, consider as G 2, and the inside region which I will mark this one, which is the feasible region. Is exactly the same type of analysis which you have done in the previous lecture. So, just highlight it using the yellow color in order to denote that this is the feasible region. Now, in case if it is deterministic, as per the norm, as we all know, it would be one of the solutions of the which is the corner point, and let us consider the corner point is this, which is the red one, which I am not going to highlight, it is already shown red. If you want, I can highlight it using the red color. So, this is the deterministic solution. So, if you go, what is noted down here is the deterministic optimum solution which you have. Now, consider as the variables are orthogonal. So, let us take, I will go one by one on the same picture, I will draw and erase also. So, please bear with me. So, I will consider blue color. So, this is the axis of x 2, considered is a normal distribution. This is the axis of x 1, again the normal distribution, and consider the normal distribution variance as same. So, obviously, you will have concentric circles. So, this I will try my level best to draw. So, as the reliability increases, the line moves. So, this is the loci of the solution for the deterministic case. In case the distributions are normal, but with different variance. So, let me now prepare the diagrams in a fresh slide. So, I will basically prepare 3 slides consecutively and then come back to this. So, it will be easy for all of you to understand. I am sure you are quite intelligent enough to understand what I want to draw, but still I want to go through the diagrams carefully. So, in the first case I will repeat it, because I thought I will draw it on the same figure, but it is getting a little bit cluttered. So, you have the axis, consider x 1, x 2, whatever it is, but I will follow x 1 here. There is no change in the concept. So, I will draw the deterministic this g 1 x and g 2 x line as this. This is the best solution for the deterministic one. This I consider as the normal distribution. This I consider the normal distribution, and consider the variances are same. So, I will have, depending on the level of reliability, these are circles consider. I am trying my level best, plus please bear with me. So, this is the loci. So, the level of reliabilities are given as alpha 1, alpha 2, alpha 3. So, what is alpha 1, alpha 2, alpha 3? I will basically mark it accordingly. So, this is for alpha 1. This is for the area 1 is basically for alpha 2. And this is for, say for example, for alpha 3. So, this I will say the reliability is the solution for alpha 1, this is the solution for alpha 2, solution means the reliable solution for alpha 3. So, I will mark them, I am just circling it with different color. This is the solution for alpha 3, this is the solution. I will use a different color if possible, please bear with me. the solution for alpha 2 and this is the solution for alpha 1. Now, consider both the mean the variances are same. Now, let me go to the variance being different one at a time. I will try to use the same color. So, this is the axis, this is the axis x1, x2. So, let me check whether I have done x1, x2, yes. Oh, another thing which I did not mark. So, this is the feasible region, the total area. This I am mentioning as G1, this I am mentioning as G2. Again I draw. Now, I will be using the color scheme similarly. So, I will be switching back to the diagram also in order to make things. This is G1, this is G2. Okay, this is the deterministic solution. So, consider this variance is large and this variance is small. So, what you will have in this region, what circles colors do you use? You use this one. So, it will be with different levels. So, this is moving like this. So, this is alpha 1 and this is S the solution which is the reliable point of alpha 1. This is alpha 2, this is a solution based on alpha 2, this is alpha 3. Solution means the best optimum solution in the reliability case alpha 3. So, alpha 1 would be this area. I am using the same nomenclature of marking in the color and same type of hashed lines also. So, this is for alpha 2 and this one is basically for alpha 3 and the coloring which I did blue, violet, green. So, I will use this is alpha 3, this is alpha 2, the solution for alpha 2 and this is for alpha 1. And your feasible region would be this. So, this is the second way of trying to consider that the variance are different. The third way, by the time you have now understood, but I will still draw it. Here the drawings may not be exact, but they should definitely give you some representation of the idea. Oh, sorry, I am using a different color. This is G1, this is G2, this is the deterministic solution. Now, here the mean value is less. This is a normal distribution, and please forgive my drawing skills. So, this has a normal distribution, but the variance is large. So, in this case, rather than having the ellipse with the major axis horizontal, the ellipse would have a major axis which is now vertical. Obviously, there would be some regions. So, there would be some boundary where it will touch. So, I am not being very specific here. So, this is so here the values of alpha change, the loci of the center, which of that ellipse or ellipsoid whatever it is in higher dimension, that keeps changing. That means, that overall path will trace out that as the level of reliability changes, how the solution changes. Okay, I did not mark this. This is x1, this is x2. This would be alpha 1 for alpha 1, this one would be for alpha 2, and this one is for alpha 3. So, I will mark it alpha 1, S of alpha 1, and this area is alpha 1. This second circle is with alpha 2, and the solution is S of alpha 2. Third circle, ellipse is alpha 3, solution is S alpha 3. So, I need to mark the solutions. What color do I use? It should be blue, violet, green. So, sorry for that. So, blue, violet, green. So, I will use blue one, then the violet one, and the green one. So, you get the solution here. So, the first diagram, and obviously, I should mark this is the feasible region. So, it would look, considering the different nomenclatures, I think it should be now clear to you that for the symmetric distribution, consider the normal case as the one which gives us the best understanding. So, this is the feasible region. So, this gives so in the similar way, I should mark it properly. So, this is the feasible region. So, and in the similar way for the first diagram also, I am going my speed is a little bit slow for this lecture, because I thought I should, the diagrams will come up again, but there would be very concise. So, I thought I will explain it here such that the clarity of the concepts are absolutely clear in all the sense that how you solve. So, this is for the both the variance being equal, this both being unequal, this is also for both being unequal. Let me come back to the first diagram where we left. So, this is also not complete. So, I'll come back to this now. Consider the distributions are non-normal. Let me use the color race. It can be either left skewed or right skewed, doesn't matter. Consider this is like this. So, if these two distributions which are orthogonal, they merge, then the overall area which we see is no more a circle. So, it would be a very weird area which I have tried to draw in this figure in the 2 dimensional case. In that higher dimension case, it would be a complicated surface, and obviously, the properties of convexity and all these things should hold such that you can find on the optimization, but they would not be any more a circle of a sphere or half a sphere. So, the reliable solution for a particular value of alpha is given, and you have the feasible region which is inside. So, this is the feasible region. So, the yellow color should basically make things clear to you. So, here is alpha, and the area which you have as the reliability changes. So, you will basically have for alpha 2, alpha 3. So, this is the solution for S alpha 2, this is the solution for S alpha 3. So, this loci which I have drawn would basically be like going like this. So, with this I will end this lecture, 54th lecture, and continue more discussion about the reliability concept from the mathematical point of view, and discuss few optimization problems in the subsequent class. Thank you very much, and have a nice day.